Building a house is hard. Building one on the moon, no air, 1/6 gravity, lethal radiation, and dust that can wreck your lungs is insane. In this video, we'll break down how humans will actually pull it off, step by step, turning grey rock and ice into the first real off-Earth home, and why surviving there means rewriting almost everything we think we know about living in a house. A radio signal from Earth takes about 1.3 seconds to reach the moon, and 1.3 seconds to come back. So every question, every command, every "did that work?" has a delay of about 2.6 seconds round trip. That sounds short, but for control it's huge. You can't drive a rover like a remote control car, you can't fly a crane by hand from Earth, you can't rely on a ground team to catch problems in real time. So the first lunar house has to be run locally. The crew on the moon, or the robot controllers on the moon, have the final say. Earth can advise, send procedures, send software updates, but it can't reach in and instantly fix anything. That changes how you design every subsystem. You need clear interfaces, easy to swap parts, and layouts that a tired human in a bulky suit can understand fast. And because it's so far, resupply is slow and expensive. You don't get rush delivery of a replacement pump. A single cargo lander might carry 20 tons, about the mass of a loaded school bus, and cost hundreds of millions of dollars. You're not going to use that to ship spare couches. You ship small, dense, critical items, electronics, medical gear, tools and materials you absolutely cannot make from local resources. That means the first house has to be over-designed for repair, not comfort. Panels unscrew, racks slide out, pipes disconnect with standardized fittings. If something fails, you fix it with what you already have, or you go without. So distance and delay lock in one reality. The first people on the moon live in a semi-isolated machine that must be kept alive mostly by the crew themselves. Now add another layer of difficulty. The moon doesn't even pull on your body the way Earth does. Here's the next question. What does a normal day feel like when your body only weighs 1/6 of what it does right now? On Earth, gravity is about 9.8 meters per second squared. We call that 1 g. On the moon, it's around 1.62 meters per second squared, about 1/6 g. Your mass doesn't change. If you're 80 kilograms on Earth, you're still 80 kilograms there, but a scale on the moon would show a weight equal to about 13 kilograms, roughly 29 pounds. At first, that feels great. You can carry heavy tools more easily, jump higher, and move bulky equipment with less strain. But your body reads that weaker pull as an excuse to relax. Bones start to lose minerals, getting thinner and more fragile. Muscles, especially in your legs and back, weaken if you don't push them hard. Your heart and blood vessels adapt to doing less work, and that's not what you want if you ever come back to Earth or deal with an emergency. So the first lunar house has to bake exercise straight into daily life. You need resistance machines that give you the same kind of load your legs feel in Earth gravity. You need treadmills with harnesses that pull you down so running still challenges your beers. You might add compact centrifuge devices for short sessions of higher G on your body, especially for research or long missions. This turns part of the house into a small gym, but not a luxury one. It's more like a medical prescription. Every crew member gets a strict exercise schedule, measured output and constant monitoring. If you skip too many sessions, your bone density and muscle strength start drifting in the wrong direction. And in low gravity, that happens faster than you'd like. The house isn't just keeping air in, it's trying to keep your body from decaying in a 1/6 g environment. But even if you keep your muscles strong, you still have to deal with the moon's surface environment itself, which swings between extremes that most buildings on Earth never see. So what happens to a house when one side is hot enough to stress metals, and the other side is cold enough to freeze air solid? Near the lunar equator at local noon, the ground can reach around plus 127 degrees Celsius, about 260 Fahrenheit. Just before sunrise, it can drop to about minus 173 Celsius, around minus 280 Fahrenheit. That's a span of roughly 300 degrees Celsius from day to night. On Earth, air smooths temperature shifts. Convection moves heat around, wind mixes warm and cold layers. On the moon, you don't get that. There's almost no atmosphere, so if one part of a structure is in sunlight and another part is in shadow, they can drift to very different temperatures. Materials expand when they heat up and contract when they cool. If you don't design for that, joints crack, seals open, and pipes leak. Engineers deal with this in two main ways. First, they bury as much of the habitat as possible in regolith, the layer of lunar dust and crushed rock. A few meters of this acts like a thermal blanket, turning huge swings at the surface into slower, smaller swings around the buried walls. Second, they install active thermal control just like on a spacecraft. You have radiators pointed at black space to dump waste heat, and electric heaters and insulated lines to keep water, air and electronics from freezing during cold periods or in shaded zones. All of this costs power. Over a lunar day, which is about 29.5 Earth days, your thermal system has to constantly move heat out of the habitat or into it, or both at once in different places. That's kilowatts of heating and cooling hardware running almost all the time just to keep the inside near room temperature. So now you're far from Earth, working in weak gravity and fighting violent temperature swings. The next constraint is even simpler and harsher. There is no outside air, and that turns your entire building into a high-pressure container that always wants to fail. On the lunar surface, external pressure is extremely close to zero. Inside your habitat, you'll probably run something like 50 to 70% of Earth sea level pressure using a nitrogen-oxygen mix, or even close to full Earth pressure, to keep breathing and decompression simple. In either case, you have tens of thousands of pascals pushing outward on every square meter of wall. If you think in simpler terms, take a patch of wall 1 meter by 1 meter, a bit over 3 feet by 3 feet. At Earth-like internal pressure with vacuum outside, that patch feels a force roughly similar to the weight of about 10 tons under Earth gravity, so think in the range of 20,000 pounds. Spread that over the whole habitat and your structure is always under a heavy load. This is why engineers favour curved shapes, like cylinders and domes, rather than big flat panels. Curved shells distribute stress more evenly and keep most of the material in compression, which metals and composites handle better than tension. The first house's pressure hull will be tested on Earth to pressures higher than its normal operating point, to make sure it can survive leaks, temperature swings, and small impacts without bursting. And that brings us to the last piece of this first section. Even if the structure holds, the environment around it is still hitting you with radiation and tiny high-speed projectiles every day, forever. Away from Earth's magnetic field and thick atmosphere, the lunar surface is exposed to galactic cosmic rays and high-energy particles from the Sun. Over long stays, an unshielded astronaut on the surface could receive doses on the order of a few tenths of a sievert per year, several times higher than typical professional limits on Earth. On top of that, strong solar storms can spike the dose sharply in a short time. That pushes the first house toward heavy shielding as a mandatory feature, not an optional upgrade. Then there are micrometeorites. These are tiny pieces of rock and metal, some smaller than a grain of sand, hitting the moon at speeds from about 20 to 70 kilometers per second. That's 12 to 43 miles every second. Even at small sizes, the energy of impact is high enough to pit metal, damage coatings, and over long periods weaken exposed surfaces. So the design solution is clear. You cover the pressure hull with thick layers of regolith, maybe 2 to 3 meters deep, 6 to 10 feet. That much mass dramatically cuts radiation levels, absorbs micrometeorite hits, and also helps with temperature control. From the outside, the house is mostly a mound with access points and maybe a few exposed structures like airlocks, antennas, or radiators. From the inside, it feels like a compact, sealed, high-tech interior under several meters of rock. So by the end of just this first look, you're already dealing with distance, signal delay, low gravity, extreme temperatures, vacuum pressure loads, radiation, and constant micrometeorite exposure. The logical next question is simple and brutal. Knowing all of that, where on the moon do you dare to put the first house so that you don't make all of those problems even worse? If most of the moon is trying to break your house? The first real question is there any patch of ground that actually helps you survive, instead of making everything harder? The first big choice is simple on paper, but critical in practice. Do you build on the side that can see Earth, or the side that can't? The near side of the Moon has direct line of sight to Earth. That means you point an antenna at home, and as long as Earth is above your horizon, you have a signal. No relay satellites, no extra failure points, just a clear radio path. When something goes wrong, you can talk to mission control in real time, plus that 1.3 second delay. The far side is different. It is great for radio telescopes, because Earth's noise is blocked by the whole Moon, but that's exactly why it's bad for your first house. Without a network of relay satellites around the Moon, the far side is a communications dead zone. If your main antenna fails, or your relay satellite goes down, you're cut off. For the first crew, you already have huge unknowns, new hardware, harsh environment, long stays. Adding untested global relay system on top of that is one too many new risks at once. So the first generation habitat almost certainly goes on the near side. You accept that decision up front, because it lowers the number of new systems that can kill the mission. Later, once you have proven hardware and a support network, the far side becomes tempting. But for house number 1, you keep the communications path as simple and robust as possible. That still leaves a massive area, thousands of kilometers across. So the next question is, where on the near side can you keep the lights on without hauling a mountain of batteries from Earth? Around the lunar equator, the pattern is brutal. About 14 Earth days of daylight, then about 14 Earth days of darkness. Solar panels work well for half the month, then they do almost nothing for the other half. To bridge that night with batteries, at today's energy densities, you'd need tens of tons of battery mass even for a modest outpost. That is too much mass to waste. Near the poles, especially the South Pole, the geometry changes. The sun moves in a low circle around the horizon, instead of rising high and setting deep. Some ridges and crater rims stay lit for most of the lunar year, up to 80 or 90% of the time. These are often called peaks of almost eternal light. They are not perfect, you still get short dark periods, but compared to 2 weeks of night, they are extremely attractive. Building the first house near one of these high spots means your solar panels get a nearly continuous trickle of power. You still need some batteries and maybe backup power, but the total mass is far lower. Temperatures on those ridges are also more stable than down in the craters or at the equator, which reduces thermal stress. In simple terms, a polar ridge gives you a more constant power supply and a calmer thermal environment, both of which your life support systems desperately need. But power is only half the stew. Without local water, you're flying almost every kilogram of water and oxygen from Earth, and that does not scale. So the next issue is blunt. Where do you find water that doesn't boil away in vacuum? Near the lunar poles, inside deep craters, there are regions that sunlight never reaches. The crater walls block the sun at every angle, year-round. These permanently shadowed regions sit at temperatures below about minus 200 degrees Celsius, around minus 328 Fahrenheit. At those temperatures, water ice is stable for billions of years. Orbital data from missions like Lunar Prospector and Lunar Reconnaissance Orbiter suggest there are billions of tons of warm ice mixed with the regolith in these dark areas. For your first house, that ice is everything. You melt it for drinking water. You split it into hydrogen and oxygen with electrolysis for breathing and for rocket propellant. Oxygen also feeds your life support systems, and hydrogen plus oxygen stored as cryogenic propellants can refuel landers. That means you can launch from Earth dry and tank up on the Moon, which changes the whole logistics picture. This is the difference between a small temporary science outpost and a base that can grow. If you have to ship every litre of water, you are forever limited by launch costs. If you can mine water locally, you can support more people, more missions, more industry without multiplying launch mass from Earth. So the ideal neighbourhood is somewhere that combines near continuous light on a ridge, with access to ice in a nearby crater. There's a catch though. The places that are great for light and ice can be terrible for landing. So now you have to ask, can you actually put a lander down safely in this ideal spot, or are you trying to land on the side of a cliff? Landers like flat, boring terrain. You want slopes under about 8 to 10 degrees and low boulder density. Big rocks, steep slopes and sudden drops are all problems because a lander coming down with 15 to 30 tons of mass, roughly 16 to 33 short tons, has a lot of momentum. If one footpad hits a rock, or if the surface gives way unevenly, the whole vehicle can tilt or even tip. From orbit, we already have detailed elevation maps from laser and radar instruments, with resolutions on the order of a few meters. These maps let mission planners pick candidate landing zones, rectangles or ellipses on the order of tens to hundreds of meters across, where the slope is low and the rock count is manageable. High-resolution imagery helps confirm there are no hidden hazards. On top of that, modern landers will probably use onboard cameras and LiDAR during descent to detect boulders and pick a safe touchdown spot within that zone. So your future address is basically a flat patch that meets strict slope and rock limits, close enough to both a sunlit ridge and a shadowed crater, and reachable by rovers. The landing site choice is a compromise between safety, power, and resources. Even if you find that balance, you still face one more planning problem. The good light and the good ice may not sit in the same exact location. So you have to deal with the question people almost never think about in space. What does a commute look like when stepping outside without a suit is instantly lethal? Your main solar power station might sit up on a sunlit ridge where panels see the sun most of the time. Your mining and processing gear, the machines that dig icy regolith and melt it, probably have to operate down in a shadowed crater, maybe 10 or 20 kilometers away, about 6 to 12 miles. At a travel speed of around 20 kilometers per hour, roughly 12 miles per hour, a pressurized rover can cover 10 kilometers in about half an hour. That's fine on paper, but now you have to make that trip safe and repeatable. You grade paths so rovers don't hit hidden slopes that could flip them in low gravity. You place navigation markers, maybe reflectors or small beacons, because in a shadowed crater visibility can be close to zero. You might bury power and data cables along parts of the route, so your mining gear can pull energy directly from the ridgetop plant and stream data without relying only on radio. That commute becomes part of the base's core design, with designated emergency shelters or backup air supplies along the way. A stuck rover, a suit leak or a power failure is not a minor traffic issue, it's a life-threatening event. So the first lunar neighborhood is not just a point on a map, it's a connected system, ridge, crater, landing zone, roads, cables and shelters, all tied together. And once you understand how tight that network has to be, you hit the next hard wall. Every kilogram of rover, cable, solar panel and habitat you're spreading around that neighborhood has to be lifted out of Earth's gravity well first, fighting the rocket equation the whole way up. Here's the uncomfortable truth you run into next. How do you build a house in a place where every single kilogram you launch is insanely expensive before it even leaves the ground? Getting 1 kilogram into low Earth orbit already takes a huge amount of energy and money. You're accelerating that mass to several kilometers per second, burning through propellant and paying for a whole rocket and support system just to give that kilogram a chance to go further. Then, to reach the moon and land softly, you add another big chunk of velocity, which means even more propellant, bigger tanks, stronger engines and more cost. So when you think about a brick for your lunar house, you can't treat it like a cheap unit from a hardware store. By the time that 1 kilogram brick sits on the moon, the launch and transport have cost far more than the brick itself, by a factor of hundreds or thousands. Shipping stacks of building materials from Earth starts to look ridiculous. The math pushes you to a different strategy very quickly. Instead of sending bricks, tiles and ready-made walls, you send machines that can use local material. You trade raw mass for capability. Every kilogram you launch has to do more than one job. A robot that can dig, crush and process regolith is worth far more than a container full of pre-made blocks, because once it's there it can keep working for years. And that leads straight into the next hard question. When you only get to send a limited mass, how do you decide what makes the cut and what stays on Earth? no matter how nice it would be to have? Take a typical heavy-lift lunar lander concept. Maybe it can put around 20,000 kilograms on the surface, about 20 tons, similar to the mass of a loaded school bus. That sounds like a lot until you start listing everything you need. Life support hardware, air and water tanks, pressure hull structure, power electronics, batteries, rover parts, food, tools, scientific instruments, radiation shielding, and the crew themselves with their suits and personal gear. The numbers add up fast and your safety margins have to stay healthy. So planners build what's called a mass budget, usually in a big spreadsheet. Every subsystem gets a line with an estimated mass, an uncertainty, and some margin on top. The house exists as numbers first, not as a cozy 3D rendering. When the total starts to creep over that 20-ton limit, things get cut or redesigned. A heavier exercise device might mean a lighter interior panel. A more robust water recycler might force you to trim non-essential tools. This is where the idea of nice to have mostly disappears. A decorative element, an extra window, an oversized private cabin, all of those are competing directly with spare filters, backup oxygen tanks, or additional radiation shielding. 1 extra kilogram of furniture is 1 less kilogram of safety. For the first lunar house, comfort is built only after survival and repairability are covered. Even if you optimize every kilogram, flying directly from Earth orbit to the surface in one shot still burns a lot of propellant. So the next step is obvious. Can you break the trip into stages and reuse parts of the system, instead of treating every landing like a one-way disposable stunt? A more efficient architecture uses staging through lunar orbit. The sequence looks like this: launch from Earth, get into Earth orbit, then push out to the moon and break into lunar orbit instead of going straight down. In that orbit, you can park cargo, fuel, and maybe a small space station, sometimes called a gateway. From there, specialized landers go up and down between orbit and surface, refueling between trips. This is like having a rest stop in space. Cargo ships from Earth only have to reach lunar orbit, then hand off their payload. The landers are designed to operate in the lunar gravity field and vacuum, and they can be reused multiple times. That spreads the development cost over many missions and lets you pre-position big items in orbit, ready to go when the surface base can use them. But getting to orbit is only half the challenge. The real pain comes when you try to bring tens of tons of hardware down onto a rough, dusty surface without destroying it. So the next problem is brutal. How do you drop a small building's worth of mass onto the moon and have it arrive upright, intact, and not buried under its own dust cloud? To land heavy payloads, your engines have to throttle over a wide range. At the start of descent, you need a lot of thrust to slow down, but as you get close to the surface and burn off propellant, the vehicle gets lighter. Near touchdown, if you can't throttle low enough, you either slam into the ground or hover too high and run out of fuel. So deep throttling, restartable engines are mandatory. Guidance is just as important. The lander needs cameras, radar, and LiDAR to read the terrain below it in real time. It has to spot boulders, craters, and slopes, sometimes down to the scale of a car or smaller, and adjust its path quickly. You don't want to discover a hidden rock under one of your landing legs when 20 tons are hanging above it. Landing legs themselves must absorb the final impact. Typical touchdown speeds are on the order of a couple of meters per second, a few miles per hour, but with huge mass behind them. The legs need crushable or spring elements that take that energy without bouncing the lander back into the air. They also have to spread the load over the soft regolith so the vehicle doesn't sink or tip. Then there's the dust. Rocket exhaust at the surface accelerates loose regolith to high speeds, hundreds of meters per second. That dust cloud can sandblast nearby equipment, scour cables, and reduce visibility to almost zero. For a base with multiple landings, this is dangerous. The solution is to prepare landing pads ahead of time, either by compacting the soil, laying down mats, or eventually printing solid surfaces from sintered regolith. Some missions may even land farther away from the main habitat and use rovers to bring cargo in, just to keep the dust threat away from critical systems. Even if you solve all that, the rocket equation never stops punishing you as long as you ship finished hardware. So the last key idea in this section is the only real way to break that pattern. Can you turn the moon itself into your supplier and stop using rockets as delivery trucks for rocks and metal? This is where in situ resource utilization, or ISRU, takes over. Instead of bringing building materials, you bring machines that can harvest and process what's already there. Lunar regolith can be melted or sintered into bricks, tiles, and structural blocks. Water ice from shadowed craters can become drinking water, oxygen, and hydrogen fuel. The metal content of the soil, including iron, aluminum, and titanium, can be extracted and turned into beams and parts. Picture sending a 2-ton excavator and a 1-ton processing plant, about 3,000 kilograms total. That's a big investment, but once they're operating, they can move and process thousands of tons of local material over a few years. Instead of paying to launch every ton of shielding, you let the machines pile regolith over your habitat. Instead of flying all your propellant from Earth, you gradually ramp up local production for landers and maybe even for return trips. This is how you cheat the rocket equation. You accept that launches from Earth will always be expensive, but you use those launches to put factories, not finished products, on the moon. One very costly kilogram in the form of a robust robot or a critical reactor unlocks 1 million cheap kilograms already sitting on the lunar surface as dust and ice. And once you've committed to building your house with locally processed rock, powered by locally captured sunlight and maybe nuclear reactors, the order of operations becomes obvious. Before you can live there, you have to power it. And that means your first real construction project on the moon isn't the house at all. It's the power plant that keeps the house alive. How do you live in a place where losing power isn't an inconvenience? It's a direct path to dying in a metal can. Before the first house goes up, you have to solve one problem first: how to feed it electricity. Every hour, forever. On the moon, the sunlight hitting the surface is almost the same as what hits the top of Earth's atmosphere. Around 1,360 watts for every square meter at local noon. That's the raw energy coming in. Real solar panels are not perfect. With efficiencies around 20 to 30%, you only turn a fraction of that into usable power. Roughly 270 to 400 watts for every square meter of panel in ideal conditions, when the sun is high and the panel is clean and pointed correctly. So if your outpost needs about 10 kilowatts of power, think of that as the continuous draw of a small but very efficient building. You're looking at on the order of 30 to 50 square meters of panels, something like 320 to 540 square feet. That's roughly the floor area of a small apartment, but laid out as solar arrays instead of rooms, and that's just to meet the basic power demand. You probably want more to cover inefficiencies, storage, and growth. That means your first construction step before people move in is deploying and wiring those arrays. Robots or later crew will place them on stable ground, angle them to catch the low polar sun, and connect them back to power conditioning units and batteries. Those units convert the variable output from the panels into steady, usable power for life support, computers, and everything else in the base. So far this sounds manageable, but everything falls apart the moment the sun goes away for a long time. Away from the poles, that is exactly what happens every month. A day that lasts 2 weeks, followed by a night that also lasts 2 weeks. At those latitudes, your panels sit in darkness for about 14 Earth days at a time. To keep a modest outpost alive through that entire night using only batteries, with today's technology, you need a ridiculous amount of stored energy. Typical space-grade batteries store maybe 200 to 300 watt-hours per kilogram. When you add up the total energy needed to run life support, communications, heating, and basic systems for 2 weeks straight, you end up needing battery mass in the tens of tons, comparable to or more than the mass of the entire habitat. This is one of the main reasons polar sites look so good. On a high ridge near the lunar South Pole, the sun dips but doesn't vanish for weeks. You still get short periods of shadow or low-angle light, but not endless night. Smaller battery banks can bridge those short gaps. Still, even at the poles, relying only on solar and batteries is risky. A dust problem, a panel failure, or a long shadow event could still put you into a power crunch. So the next escalation is clear. You add a power source that doesn't care if it's day or night, or if the panels are dusty, or if the sun is behind a crater rim. That's where compact nuclear reactors enter the picture. Small fission reactors in the 10 to 40 kilowatt range are already under study for space missions. 10 kilowatts is enough to support a minimal outpost. 40 gives you breathing room and growth. These units can be built into packages with total masses of just a few tons, including shielding and power conversion systems. For comparison, that's similar to a large SUV or a big pickup in mass. On the Moon, you don't want the crew living right next to the reactor. You place it a safe distance away, maybe tens or hundreds of meters, tuck it into a trench or behind a thick berm of regolith, and run cables back to the habitat. The regolith itself becomes part of the radiation shield. Once activated, a well-designed reactor can provide steady power for years with no refueling, running pumps, fans, heaters, lights, and communications without caring whether the sun is up. For your first lunar house, this is the difference between shutting almost everything down during long dark periods and living in survival mode, versus keeping a normal operating profile. With nuclear in the mix, you don't have to gamble the entire base on perfect solar performance. All of this is necessary because the house itself is much hungrier than a normal home on Earth. A typical single-family house might use a few kilowatts in peaks and much less on average. Your lunar habitat burns through more, and it never really gets to turn off. Life support systems need pumps to move water and air, compressors for oxygen handling, and active scrubbers to remove carbon dioxide. Those alone can draw a few kilowatts continuously. Heating and cooling to keep the temperature comfortable inside take more. Lighting, even with efficient LEDs, still adds up when you consider workspaces, sleeping areas, and growth modules. Communications gear talking back to Earth and to local systems adds its share. Computers, scientific instruments, exercise equipment, cooking appliances all stack on top. For a small crew of 4 to 6 people, a realistic continuous power budget sits in the range of 10 to 20 kilowatts, 24 hours a day, 7 days a week. That's closer to the load of a small data center or a telecom site than a normal house. And that budget must include margin, because any spike or overload that trips systems at the wrong time could directly hit life support. So every new device is questioned. How many watts does it draw for how many hours per day? What happens if it fails? And what happens to the rest of the system if it fails in the worst possible way? The first house is wired like a critical facility, not like a casual building with a few power strips. As if that wasn't enough, the environment does its best to attack even your power infrastructure. The Moon's dust is electrically charged, sharp and sticky, settles on panels, cuts into seals, and can cause short circuits if it gets into connectors. That forces you to treat cables and panels in a way that looks more like ship or spacecraft design than ordinary construction. Power cables are likely buried under a layer of regolith. That keeps them out of direct radiation, protects them from micrometeorites, and shields them from dust transport during landings and rover operations. Connectors are sealed and standardized so one failed cable segment can be swapped or bypassed. Solar panels may need active dust removal, from simple brushes and wipers to more advanced electrostatic systems that shake dust off using electric fields. Inside the habitat, you don't run a single main bus that everything depends on. You run multiple power buses in separate routes with automatic breakers and isolation. If one circuit shorts, the others keep feeding the critical loads. Essential systems like life support and communications sit on the most protected, redundant feeds, often with their own small local battery backups or a flywheel storage. The standard for this is not residential code, it's closer to how you wire a ship or a spacecraft, where fire, shorts and overloads have to be contained instantly. On the Moon, a single unprotected power line is a liability. A single point of failure in your energy system is basically a loaded gun pointed at the crew. So by the time the first people walk into their house, an entire power grid will already be in place, spread across the regolith, tied into sunlit ridges and nuclear units in trenches, defended against dust and overloads. Only then does it even make sense to talk about anchoring a structure into that ground, which raises the next question. What does it mean to build foundations and walls on soil that isn't really like sand or dirt at all, but more like a layer of crushed glass that's been hammered for billions of years? The ground under your feet on the moon looks like dust, but it does not act like beach sand. And that matters a lot when your life depends on not sinking, tipping, or tearing your house apart from below. Lunar regolith, the surface layer, is made of grains smashed by micrometeorite impacts for these billions of years. There's no wind, no water, nothing to tumble and smooth the particles so they stay sharp and jagged. Grain sizes range from tiny micrometers, smaller than a red blood cell, up to a few millimeters, similar to coarse sand or small gravel. In loose form, that mix has a bulk density around 1.5 grams per cubic centimeter, lighter than solid rock, heavier than fluffy soil. When it's been compacted by repeated impacts or by weight over time, it can reach around 1.9 grams per cubic centimeter. Step on it in a spacesuit, it compresses under your boots, but it doesn't puff away like powder. Try to dig in it, and it can clump, shear, and collapse in strange ways, something between talc and broken glass. This is not material that behaves like the soil civil engineers deal with every day on Earth. Any construction plan has to be based on real measurements and tests, not intuition from backyard dirt. That leads straight to the next concern. You're going to bury and support a pressurized habitat in this stuff. So can it actually hold the load without everything slowly sinking or tilting over months and years? Despite looking like a layer of loose dust, the upper regolith does have real bearing strength. The Apollo lunar modules weighed several tons each, thousands of kilograms in moon gravity, and their footpads only sank a few centimeters into the surface. That tells you the soil can support substantial loads if you spread them out properly. For design, engineers talk in terms of pressure, kilopascals, how many thousands of newtons per square meter the ground can take. Compacted regolith can reach static bearing capacities in the tens to low hundreds of kilopascals. For a buried low-rise habitat with a rounded pressure shell and wide foundations, that is enough, as long as you don't concentrate all the weight on a few small points. So the first house won't sit on skinny stilts. Its load gets spread across broad-based plates, printed slabs, or continuous rings, so the pressure per square meter stays inside safe limits. Robotic tests, maybe with heavy test masses and load cells, will happen before any crew habitat is placed to confirm the local regolith's behavior, layer depth, and strength. If a spot is too weak, they move, or they compact it more before committing. Even if the soil holds your weight, you can't assume the ground is perfectly still forever. The moon is quieter than Earth, but not motionless, and that means the house has to handle occasional shaking without cracking its pressure hull. The moon has moonquakes, different from typical earthquakes. Some are caused by tidal forces from Earth, some by thermal expansion and contraction, some by meteoroid impacts. Shallow moonquakes can reach magnitudes around 5 on the same scale we use for earthquakes. Not catastrophic, but strong enough to matter. Because the moon's crust is rigid and there's little internal damping, the shaking can ring for longer than we're used to. So you do not bolt the house down as if the ground is perfectly rigid. You design in flexible joints and shock-absorbing supports between the regolith foundation and the pressure modules. Think of layers of crushable or springy material, not to save furniture, but to keep structural loads within safe ranges when the ground slowly shifts a few millimeters or vibrates for minutes. The good side is, there are no tectonic plates, no hurricanes, no floods, no erosion from rivers, so once you design for moonquakes and impacts, most of the major ground threats are covered. But you still assume the surface can kick you occasionally. There's another twist. Your habitat is like a balloon under high internal pressure. And in low gravity, that balloon wants to rise even when you bury it. In 1/6 g, the same mass pushes down with only 1/6 the force, but the internal air is still pushing out full strength. A pressurized cylinder or dome under a layer of regolith experiences an upward lift force, because the internal air is trying to expand the volume, while the weight of the structure and overburden is holding it down. If the regolith shifts, or if part of the shell is exposed, some segments could start to lift or flex. To prevent that, you don't rely only on mass, you physically anchor the structure to the ground. Anchors can be deep-driven piles that go down into more compact layers, tied mechanically to the pressure hull. They can also be massive regolith-filled bags or blocks set around and over the habitat, acting as counterweights that can't easily slide away. In some places, if bedrock is shallow enough, you might even 3D print or melt foundations that fuse to it, turning the base into one combined solid. Geometry matters. Wide flanges, broad plates, and interlocking shapes all increase friction and locking strength, so even in 1/6 G, the house stays put. All of this foundation work depends on one basic job getting done first: turning the landing area from a messy cratered patch of alien dirt into something that heavy machines and humans can actually operate on without constant risk. Before any crew sets foot on the site, robots will spend months to years grading it. They'll use blades, rakes, and compactors to shave off small bumps, fill shallow craters, and compress key paths. Even a height difference of a few centimeters over 10 meters, say an inch or two over 30 feet, can change how regolith erodes under lander exhaust, or how a wheeled rover behaves when turning with a heavy load. They'll carve out dedicated zones, a flat pad for landers, stable routes for cargo rovers, slightly raised platforms for power equipment, and depressions for buried cables and pipes. The habitat area will likely sit on a controlled leveled patch, maybe rimmed with low berms to stop drifting dust and debris. Drainage in the usual sense doesn't matter. There's no rain, but the way dust moves under thrust and under rover tracks absolutely matters. By the time a human crew arrives, the front yard will look more like an industrial worksite than an untouched landscape, with flattened strips, compacted zones, marker posts, and hardware already half buried. That prepared ground is what lets you start thinking about printing walls and arches from the soil itself. And that leads to the next step in this chain. Once you trust the ground to hold you up and stay mostly stable, how do you actually turn this sharp, abrasive dust into solid structures strong enough to shield you from radiation and impacts without hauling cement or steel from Earth? You already know you can't afford to ship bricks and concrete from Earth, so the next step is harsh but simple. You have to turn the moon itself into your building material. The question is, can that sharp, dusty regolith actually behave like a real construction material strong enough to hold thousands of tons above your head? On Earth, engineers don't wait for the first mission to find out. They use lunar regolith simulants, mixtures of crushed rock with similar chemistry and grain sizes to what Apollo brought back. In labs and test fields, they've already run 3D printing experiments. They spread thin layers of this simulant, then heat it with focused sunlight or microwaves until the grains partially melt and fuse. The result is blocks, arches, and tiles with compressive strengths in the range of a few tens of megapascals, similar to weak concrete or some strong brick. That's not good enough for skyscrapers, but it is more than enough to build thick shells, arches, and protective berms in 1/6 G. It proves a basic point. You can literally bake lunar soil into structural elements without shipping cement, steel rebar, or epoxy from Earth. The moon's dust can become your outer walls. Once that's on the table, the next decision is about chemistry and logistics. What exactly is going to hold your printed walls together, and does it cost you launch mass, or just power? If you bring chemical binders from Earth, like resins or epoxies, you gain some control and maybe better strength, but you lose the whole point of in situ resource utilization. Every kilogram of binder has to ride a rocket, and you will always need more as you expand. That doesn't scale, so the leading approach skips imported binders and uses sintering instead. Sintering means heating the regolith grains until just their surfaces soften and fuse without fully melting the entire volume. With microwaves, you can push temperatures past 1000 degrees Celsius over 1800 Fahrenheit inside the soil itself. That creates a glassy or ceramic-like solid, hard, brittle, and very tolerant of vacuum and radiation. No solvents, no outgassing, no weathering. The trade-off is energy. Every square meter of wall, every arch and beam costs you kilowatt hours of electrical power. On a planet with cheap grid power, that's nothing. On the moon, where every watt comes from solar arrays or a reactor you launched at huge cost, energy is precious. That means printer duty cycles, power availability, and build sequences all have to be planned like a factory schedule, not like weekend construction. So then you get to the practical part. What sort of machines actually do this printing in 1/6 G, in vacuum, in dust, with no one standing next to them to babysit? You're looking at squat, tough robots, maybe around 500 kilograms each, roughly the mass of a small car engine or a big motorcycle. They move on tracks or wide wheels, keeping ground pressure low so they don't dig themselves into the regolith. Up front, they carry a hopper and a controlled spreader head that lays down thin layers of loose soil, 1 to 2 centimeters thick, less than an inch, in precisely defined paths. Right behind that, a microwave or laser unit sweeps across the layer, heating it until the grains fuse into a solid strip. Print speeds are modest, a few centimeters per second along a path, but continuous. One robot can slowly trace ribs, ring segments, and surface tiles, layer by layer, building up walls, arches, and domes over days to weeks. With 2 or 3 units working in parallel, a small protective shell can go from bare ground to full coverage in a matter of weeks, not years. Because it's all done before humans arrive, there's no rush, as long as the robots stay healthy and power is available. But strength isn't just a number in a lab test, it's about thickness and geometry. So the question becomes, how thick do these printed shells need to be to actually protect you from radiation and impacts? And does that thickness push your printers or your power plant to the breaking point? Your pressure module, the actual habitat, will probably be a metal or composite cylinder or dome just a few centimeters thick, inches at most. That structure holds the air. The regolith shell around it is there for shielding and thermal stability, not for airtightness. For radiation protection, rough targets are 2 to 3 meters of regolith overhead, about 6.5 to 10 feet. That much mass cuts the particle dose from space down to levels close to what astronauts see in low Earth orbit, maybe even lower depending on design. Structurally, a scintillated arch 50 to 100 centimeters thick, half a meter to a full meter, around 2 to 3 feet, is extremely strong in 1/6 G. It can carry many tons of overlying regolith without coming close to failure, as long as the arch geometry is correct and the printing quality is consistent. That means strength is not the main limit. The real bottlenecks are how fast your printers can lay down and fuse material, and how much power you can feed them without starving the rest of the base. So you scale your machines and schedules around that. Maybe you accept that the first shell is thinner, with only partial radiation protection, and then thicken it over time as more power and hardware arrive. Or you prioritize one storm shelter area with the full 3 meters of cover first, then expand shielding to the rest of the habitat later. Every layer is another set of printer passes and another block of energy consumption. All of that only makes sense if you send the printers years before the crew. So the last piece of this section is the build sequence, and it flips the normal mental picture completely, because by the time humans land, the house is already partly there. The robotic construction phase starts with the site preparation you already saw, grading, compacting and mapping. Then the printers move in and build a regolith hangar, basically a big arched shell with open ends or sealed trenches, sized to cover the future habitat modules. They might also print low walls, berms and cable trenches, plus pads for landing and parking rovers. Next, more specialised machines dig shallow pits or trenches where the pressure modules will eventually sit, and perhaps lay down initial foundation slabs or rings made from sintered regolith. Power lines from the solar arrays or reactors get buried and routed into this area, and basic control electronics and sensors are installed. All of this happens with no humans on site, overseen from Earth with that annoying 1.3 second delay each way, so the robots have to be able to handle routine tasks and small obstacles on their own. Only after this robotic phase is stable, after the shells are printed, the trenches are ready, and power is flowing reliably, do you send the crew. When their habitat modules arrive, They're landed nearby, then moved either by specialised crawlers or by low-friction sleds to slide into those printed garages or covered trenches. The regolith shell is then partially closed around them. Gaps are backfilled and extra shielding is piled on top. By the time you walk in as a crew member, you're not starting from bare rock and dust. You're stepping into a pressure can that slides into a stone-like tunnel that has been waiting for you for months or years. Pre-wired, partially buried, and tied into a power and communications network. Your job is not to build the house from scratch. It's to seal it, connect life support, test every joint, and bring the system fully online without breaking what the robots already put in place. And once your pressure cannon is locked inside that regolith cocoon, the next challenge becomes critical. The air inside that shell is always trying to burst it open, and any leak, crack, or puncture is not a minor maintenance issue. It's an emergency. So the design focus shifts from printing walls outside to controlling the pressure bubble inside, and making sure it can survive years of that constant outward push without failing. So how dangerous is that pressure bubble actually? And what is it doing to every square metre of your walls, every second, for years? Inside the habitat you want something close to Earth conditions, an atmosphere thick enough that you can breathe normally, talk normally, and not feel like you're in a high-altitude tent. That usually means a pressure on the order of 1 bar or maybe half to 2/3 of that. 1 bar is about 100,000 pascals, which is also about 100,000 newtons of force on each square metre of surface, roughly the weight of a 10-ton truck in Earth gravity, around 60,000 pounds. So take a patch of wall that's 1 metre by 1 metre, a little over 3 feet on a side. The air inside is pushing out on that patch with the same force as that truck sitting on it. Now spread that out over the whole inside surface of the habitat. The total force is enormous. That's why the shape of the habitat is not a style choice, it's an engineering survival choice. Flat walls focus stress into corners and joints, which is bad. Cylinders, spheres, and donut-like torus shapes spread the load. In those shapes, most of the structural material is in compression and hoop tension, which metals and composites handle well. Domes and pressure cylinders are standard because they minimise weak points and make it easier to keep stress levels within safe limits for decades. This leads straight to the most practical design for the first house, a strong pressure can inside, with the regolith shell outside acting like armour, not like a second hull. A realistic early habitat is a metal or composite module somewhere between 4 and 6 metres in diameter, about 13 to 20 feet and maybe 10 to 15 metres long, around 33 to 50 feet. You can think of it as a stretched cylinder with rounded ends, like a very large reinforced tank. That structure is built and tested on Earth under controlled conditions. Engineers pressurise it well above its normal operating pressure, to make sure welds, joints and seals hold. They scan for tiny cracks, they cycle the pressure up and down, they simulate temperature swings. Only after it passes those tests do they qualify it to go to the moon. Once on the surface, this pressure can does not sit naked. It gets parked under or inside the sintered regolith shell you printed earlier. The regolith outside does not have to hold air, it can leak and crack and it's still fine. Its job is to take impacts, block radiation, and help with thermal stability. That separation of roles is key. The inner shell holds pressure, the outer shell takes the hits. Of course, you still need a way in and out, and that's where the most stressed doorway you will ever use comes in, the airlock. An airlock for lunar surface work is basically a small pressure chamber bolted to the main habitat. A common size might be 1.5 to 2 metres in diameter, about 5 to 6.5 feet and around 2 metres long. 2 or 3 suited astronauts can fit in there at once. Every time they leave, the airlock goes from full internal pressure down to near vacuum. Every time they come back, it goes from vacuum back up to normal. That can happen dozens of times a day. The hatches on both ends of that airlock have to survive thousands of these cycles without starting to leak. Seals can't dry out or crack under radiation and dust. The hinges and latches have to work in bulky gloves in low gravity, possibly when people are tired or stressed. To reduce the amount of air you lose every time you open to vacuum, you probably add pressure equalization tanks, basically small side tanks that capture most of the air as you depressurize, then feed it back into the system instead of letting it vent into space. That adds plumbing and valves, but it saves a lot of oxygen and nitrogen mass over months and years. Inside, the airlock is treated less like a casual front door, and more like a clean room and a submarine hatch combined. There are strict procedures for cycling it, for brushing dust off suits, for checking seals before you open the outer door. People rehearse those steps over and over, because if you get sloppy, you risk losing air or bringing in toxic dust. Even with perfect design though, you never get a habitat that is absolutely leak-proof. Tiny leaks are inevitable, so the next question is, how do you spot them fast enough that they don't turn into a fatal pressure drop? The whole interior is filled with pressure sensors in every module and corridor. They track absolute pressure and how quickly it changes, down to fractions of a kilopascal. Software watches those readings constantly. A slow leak, maybe 1% of the atmosphere per day, is serious, but you have time to react. You can close some hatches, narrow down which section is losing air, and send a crew member with handheld detectors and foam sealant to patch it. A sudden drop is different. If pressure starts falling quickly, you don't wait and think about it. Automatic systems slam bulkhead doors shut to isolate sections. Alarms go off in every part of the house. Crew run to safe zones with independent air tanks. Leak location systems compare sensor data, listen for ultrasonic noise from escaping gas, and use that to triangulate where the breach probably is, ideally within minutes. The layout of the habitat reflects this. You don't have one big open volume with everything in it. You have compartments, each able to be sealed off. Any single puncture, from a tool accident or a micrometeorite that got through the shell, should only be able to drop pressure in one compartment, not in the entire base at once. All of this rides on one more fundamental choice: what atmosphere you actually put inside the house, because that sets both your structural loads and your fire risk. Early spacecraft used pure oxygen at low pressure because the structure could be lighter, valves and seals were simpler, and you didn't have to carry nitrogen as a buffer gas. But pure oxygen is extremely dangerous for fires. Materials that barely burn in air on Earth can burn violently in high oxygen environments. For a small, cramped habitat full of electronics, wires and plastics, that's not acceptable. So a more realistic option for a lunar house is a mixed gas atmosphere, with nitrogen and oxygen at a total pressure between roughly 50 and 70 kilopascals, about half to 70% of Earth sea level pressure. You tune the oxygen partial pressure so that it matches what your body expects at sea level or at a comfortable altitude, so you can breathe normally without long adaptation. The nitrogen mostly just adds bulk pressure and makes the total more like what your lungs, sinuses and ears are used to. Running at this lower total pressure reduces the structural load a bit compared to full Earth pressure, but it's still tens of thousands of pascals pushing on every square meter of hull. The structure has to be designed for that plus safety margins. In exchange, you get a much safer fire profile, fewer decompression sickness issues when people go in and out through airlocks, and a more normal feeling environment for long stays. However, this also means you now have two precious gases in your life support loop: oxygen and nitrogen, both of which are expensive to launch and hard to replace. Any leak is now not just losing oxygen you need to breathe, but nitrogen that sets the pressure. That keeps the pressure control problem tightly coupled to your leak detection, your resupply schedule, and your in situ resource plans. So by the time you've solved pressure, you've built a hardened metal shell, buried it in a man-made stone cave, locked it behind industrial-grade hatches, and wired it with sensors and emergency doors. But even if those walls never crack and the air never escapes, you're still under a constant invisible attack from radiation and tiny rocks moving faster than bullets, and if you don't deal with that, the crew still loses, just more slowly. On Earth, radiation is something you mostly forget about. On the Moon, it's never allowed to leave your mind, because if you get the numbers wrong, the house kills you slowly instead of quickly. Here's the scale. On Earth's surface, normal background radiation is around 2 to 3 millisieverts per year, depending on where you live. Airline crew and people at high altitude get more, maybe a few extra millisieverts. It's not nothing, but it's low. On the Moon, in an unshielded habitat sitting on the surface, long-term doses can be 10 to 20 times higher. That means tens of millisieverts per year, and during big solar particle events, you can get a sharp spike in a very short time. Those high-energy protons and heavy ions slice through tissue and DNA. Over years, that pushes your lifetime cancer risk way up. For a short Apollo-style trip, you can tolerate some risk. For a person living and working in a house there for months to years, that is not acceptable. So radiation shielding is not a future upgrade or a phase 2 improvement. It sits in the same category as air, water and pressure hull integrity. If you can't keep the crew's dose down into a controlled range, your house is just a slow, expensive radiation trap. That leads straight to the key design question: how much rock do you need over your head before the numbers look reasonable? Studies and simulations suggest that a layer of regolith, about 2 to 3 meters thick over the habitat, roughly 6.5 to 10 feet, cuts radiation levels down very strongly. With that much material overhead and on the sides, the dose inside can approach what astronauts get on the International Space Station, or even better, depending on the exact geometry and shielding layout. That still isn't Earth's background, but it's in a range we already know how to manage with medical monitoring and mission planning. The mass behind that thickness is huge, and this matters for your construction robots and your structural design. Take a modest roof area, 100 square meters, about 1,000 square feet. Cover it with 2 meters of compact regolith, that's 200 cubic meters of material. If that regolith has a bulk density around 1.8 grams per cubic centimeter, that works out to around 360 tons of mass. In 1/6 g, it weighs less than on Earth, but from the structure's point of view, the force is still large and continuous. All that mass has to be dug up, moved, and placed by your excavators and printers. They have to survive the abrasion, the thermal cycles, and the dust while moving what is basically a small artificial hill on top of your habitat. And your sintered arches and walls underneath have to carry that load without creeping, cracking, or slumping over years. Radiation numbers set that thickness target, and the target drives everything else: power, construction time, machine durability, and safety margins. Even if you get the radiation side under control, you still have another external threat: constant impacts from tiny debris moving at insane speeds. The lunar surface is bombarded all the time by micrometeorites, small grains of rock and metal, sometimes dust size, sometimes larger. Over a square meter of surface, you might see a few impacts per year from grains big enough to cause measurable damage over long timescales. Each grain can be moving at tens of kilometers per second, that's tens of thousands of meters per second, or dozens of miles every second. At those speeds, even a grain smaller than a grain of sand can punch pits into metal, chip ceramics, or damage exposed electronics. An unprotected thin metal wall, left alone for years under this constant sand blasting from space, will collect craters, dents, and potentially pinholes. That's why the sacrificial outer layer of regolith is so important. A thick, loose shell of lunar soil absorbs micrometeorite impacts very efficiently. The grain hits the outer surface, breaks apart, and its energy is spread through many particles. The chance of a small grain punching all the way through several meters of regolith, and then through your pressure hull, is extremely low. Larger rocks, real meteoroids, are rarer but much more dangerous in a direct hit. The good news is statistical. The Moon is huge, your habitat is tiny. The odds that a large rock picks the exact spot of your house in any given year are low, but not zero. That's one reason you eventually want multiple modules spaced apart, not one single habitat. If a freak impact destroys one, the others remain functional, and the crew has somewhere to evacuate. Redundancy at the level of entire buildings becomes part of your insurance policy. All of this points you toward one clear conclusion: the best place for people to live is not on the surface, it's under it. So you have to compare two options: cool-looking exposed structures versus buried bunker-like habitats that you barely see from the outside. Inflatable modules sitting on top of the regolith look great in concept art. They're visually dramatic and easy for the public to grasp, but structurally and environmentally they're a bad trade. To protect an exposed module from radiation and impacts, you'd have to build a complex layered shield around it anyway, and you'd still fight bigger temperature swings. One unlucky piece of debris or a failure in the shield could damage a large exposed area. Burying the module changes the game. Put the pressure can 3 meters below the surface, inside a printed arch, and cover it with a few meters of regolith. Radiation drops, external temperatures smooth out, micrometeorites hit the ground above you and never touch the hull. From the crew's point of view, it's quieter, darker, and more stable. From the engineer's point of view, it's simply safer. The downside is that if something structural fails, access and rescue are harder. You're designing more like underground vaults or tunnels with careful arches and supports, not random caves. Every access route, escape path and maintenance tunnel has to be mapped and reinforced. Even with heavy shielding, you still don't just hope that radiation stays low. You measure, forecast and prepare for the worst spikes, because the sun can change from quiet to dangerous in a matter of hours. Space weather monitoring becomes part of your routine. Satellites in Earth orbit or parked at Lagrange points watch the sun, track solar flares and coronal mass ejections, and send warnings when a storm is on the way. Those alerts give you a lead time, maybe hours, sometimes more, before a wave of high-energy particles reaches the moon. When that alert comes in, the crew moves into the most heavily shielded part of the habitat, a dedicated storm shelter. That area might be built under extra regolith, with thicker walls and ceilings, water tanks overhead, and possibly layers of hydrogen-rich plastics that are especially good at stopping certain types of radiation. You shut down non-essential work, cancel EVAs, bring everyone inside and ride out the storm while dosimeters monitor real-time exposure. Only when levels drop do you go back to normal operations, so even after you've piled hundreds of tons of soil on top of your house, even after you've built redundancy into the very layout of your modules, you're still living under an invisible siege, always watching the sun and the sky for events that your ancestors never had to think about. And after you've solved that, there's still one more enemy coming at you from outside every day and night cycle, not in particles or rocks, but in raw heat and cold. Even buried under meters of regolith, your house is still surrounded by a world that swings between extreme hot and extreme cold, and there is no air to smooth it out. So the next problem is brutally simple. How do you keep the inside at something like 20 degrees Celsius, 68 Fahrenheit, when just a few meters away the ground and rock are trying to drag you toward either an oven or a freezer? How do you keep a room at 21 degrees Celsius, around 70 degrees Fahrenheit, when just outside the wall the environment swings by hundreds of degrees and there's no air to carry heat away or bring it in? At the bare lunar surface, you've got that brutal cycle. At local noon, the ground can be well above 100 degrees Celsius, over 200 Fahrenheit, and before dawn it can drop below minus 170, around minus 280 Fahrenheit. That's a swing of hundreds of degrees between day and night. If your habitat sat exposed on top, your thermal system would be fighting a massive battle all the time. Burying the house under a few meters of regolith changes that. A few meters down, the temperature doesn't track every sunrise and sunset, it smooths out. Depending on the region, you might see stable temperatures somewhere around minus 20 to minus 30 degrees Celsius, roughly minus 4 to minus 22 Fahrenheit. Still cold, but now your thermal system only has to bridge tens of degrees up to a comfortable room temperature, not hundreds. That difference slashes how much power you need for heating and cooling. You still insulate the pressure hull just like you insulate a building on Earth, but the regolith around it acts as a huge buffer. It slows down how fast external changes reach you. If the surface bakes for a few days or cools for a few days, the inside of your buried shell barely notices, as long as your thermal control keeps up. The tricky part is that on the moon, you lose the easiest tool we use on Earth, air as a coolant. On Earth, buildings dump heat into moving air through fans, vents, and convection. Hot air rises, cool air comes in, and even simple window vents move a lot of energy. On the moon, outside is vacuum. There's no outside air to blow past a radiator, no breeze to carry away waste heat. You only get two ways to move heat: conduction through solid materials and radiation as infrared light into space. So your habitat uses big, finned radiators, panels with lots of surface area, probably tens of square meters angled toward dark sky so they can see cold space. Hot coolant from inside the base flows through these panels, and the panels glow in infrared, dumping heat. They might operate at 40 to 60 degrees Celsius, around 104 to 140 Fahrenheit, or even higher, because hotter radiators can throw off more heat per square meter. Internally, heat exchangers pick up energy from life support equipment, electronics, and people and transfer it into a closed coolant loop that feeds the radiators. This is a constant process. Even when the surface outside is freezing, the inside is generating heat. People are warm. Electronics turn electricity into waste heat. Pumps and fans get hot, so most of the time you're not trying to stay warm, you're trying to get rid of extra heat without dropping the interior temperature too far. Because power is finite, you don't want a system that instantly fails the moment the radiators shut down. That's where thermal mass and phase change materials come in, basically thermal shock absorbers for your house. Water is excellent for this. A few tons of water, say several thousand kilograms, stored in tanks around the habitat, can soak up huge amounts of heat for a modest temperature change. Wax-based phase change materials do something similar. They absorb large amounts of energy as they melt, at a nearly constant temperature. Regolith itself, packed around and under the habitat, also stores heat or coolness, slowing changes. When your power system is healthy and you have spare energy, you can choose to charge these thermal batteries. You might run chillers a bit harder, cooling water tanks or phase change modules down. If you lose power or have to run in emergency low power mode, that stored cool capacity gives you hours to days before the interior temperature drifts into dangerous ranges. The same works in reverse if you need to store heat. Thermal mass buys you time, and on the moon, time in an emergency is oxygen. Inside the living space, you aim for something that feels normal. Temperatures around 20 to 24 degrees Celsius, 68 to 75 Fahrenheit, and humidity in the 30 to 60% range. You don't want it too dry or your skin and lungs suffer, and you don't want it too humid or condensation and mold risk go up, especially around cooler surfaces. Air circulates through ducts at gentle speeds, maybe 0.2 to 0.3 meters per second, about half to 2/3 of a mile per hour. That's enough to feel fresh, without feeling like a constant draft. Fans, filters and ducts mix air between rooms, even out hot and cold spots, and keep carbon dioxide from building up in corners. Sensors are everywhere, not just one thermostat per room. You track temperature at the ceiling and floor, near outer walls, near equipment racks, and in sleeping quarters. You also track humidity, airflow, and even the temperatures of structural components like bulkheads and pipes. Hundreds of readings per minute feed into control software that adjusts valves, pump speeds, fan speeds, and radiator flow. Comfort becomes a control problem, not just an insulation problem. The system has to respond smoothly, without overshooting and creating hot-cold swings that stress both people and hardware. But one more coupling makes the thermal system even more critical. Heat control is directly tied into fire safety. In a closed, pressurized volume, a small fire is far more dangerous than the same fire in an earth building with open windows. In a sealed room, a fire doesn't just burn local materials, it rapidly heats the air in that room and pumps it full of toxic gases and smoke. Because there is no outside breeze and the volume is small, temperatures and gas concentrations can spike very fast. The thermal system and air handling system have to treat a fire as a critical event. That means sensors watching for unusual temperature rises, for hotspots on walls, and for rapid changes in air composition. If something starts to burn, the system can isolate that zone by closing dampers in the ducts. it can redirect airflow to push smoke into scrubbers and filters instead of letting it flood living spaces, and in extreme cases it can vent a limited amount of hot, smoky air directly into space, dumping both heat and toxic gases at the cost of losing some precious atmosphere. Fire suppression itself might use inert gases, water mist or foam, chosen to knock down flames without wrecking electronics or creating secondary hazards, and afterwards the thermal system has to bring that area back under control, cooling hot surfaces and avoiding condensation or structural damage. So by the time you have a stable 21 degrees inside, it's only because a whole chain of systems is working together: radiators, pumps, tanks, sensors, and control software. All dealing with an environment that has no air, extreme external temperatures, and no second chances when something overheats. And even with temperature, pressure, radiation, and impacts under some control, the house still isn't really alive. You still need oxygen, water, food, and a way to deal with the carbon dioxide and waste. All in a place where there's no river to drink from, no air outside, and resupply from Earth is slow and expensive. So the next challenge is harsh and simple. How do you turn this sealed, thermally stable bunker into a closed-loop life support system that can keep people breathing and eating for months, even when the rockets from home stop showing up on time? Air, water, and food are suddenly not background details. They are hard numbers you have to hit every single day, or the house stops being a home and becomes a sealed coffin. On Earth, you can ignore the chemistry of breathing. On the Moon, you track every kilogram of gas and every litre of liquid in and out of the system. Start with oxygen, because if that stops, you only have minutes. Each person uses roughly 0.8 to 1 kilogram of oxygen per day just by breathing. For a crew of 4, that's 3 to 4 kilograms of O2 every day, over a ton per year if you don't recycle or produce more. You're not going to fly that mass from Earth over and over. The primary way to get oxygen early on is from water. You use electrolysis, you push an electric current through water, and the H2O splits into hydrogen and oxygen gas. The oxygen goes into tanks and then into the habitat. The hydrogen can be stored, burned, or fed into other reactions, but electrolysis is not free. At overall system efficiencies of maybe 50 to 70%, you're spending serious kilowatt hours of power for every kilogram of oxygen you make. That power has to come from your solar arrays or your reactor, so life support and power are tied together tightly. In the longer term, you're not limited to water. Lunar regolith is full of oxygen, locked into minerals up to 40 to 45% of its mass. With molten regolith electrolysis, you heat the soil until it melts, then run current through it. Metals like iron and aluminum move one way, and oxygen's released at another electrode. That gives you two products: breathable oxygen and metal feedstock. In that sense, your walls and your landing pad are literally made of future air, if you have the reactors and power to crack them apart. Water is next. On Earth, you open a tap. On the Moon, every drop is tracked, recycled and reused until the system says it's finally time to throw it out. The International Space Station already shows what this looks like. It recovers more than 90% of its water from urine, sweat, and even moisture in the air from breath. A lunar house will run a similar system, maybe even tighter. Each person might run tens of litres of water per day through the loop, once you count drinking, washing, humidity, and system losses. That water goes through filters, distillation units, chemical beds, and UV sterilizers, then comes back as clean as or cleaner than what you drink on Earth. If the recycling is robust, a 4-person crew might be able to operate on only a few hundred litres of stored water, a couple of large household bathtubs in total volume plus whatever extra you bring or produce from local ice. Lose that recycling performance and your consumption skyrockets, and suddenly you need constant resupply or massive local production just to stay even. So water processors, pumps, valves and filters are not side equipment. They're core survival hardware. When you run all that, you're constantly pulling oxygen out of water and feeding it to the crew. That oxygen comes back out of their lungs as carbon dioxide, and if you don't manage that loop, CO2 becomes a slower but still deadly problem. Each person exhales around 1 kilogram of carbon dioxide per day. 4 people mean 4 kilograms a day. In a sealed volume, that adds up fast. Even going from Earth's tiny background level, about 0.04% CO2, up to 1 or 2%, can start to affect how clearly you think and how well you feel, especially over days. Higher levels can trigger headaches, confusion, and eventually real medical emergencies. So you run CO2 scrubbers around the clock. Some systems use solid amine materials that bind carbon dioxide when air passes over them, then release it when heated or exposed to vacuum, so you can dump the captured CO2 outside. Others, like classic lithium hydroxide canisters, bind CO2 in a chemical reaction, but those are single-use, so they're better as backups. For closed loops, you add Sabatier reactors. They take CO2 and hydrogen and react them to form methane and water. The water goes back into your electrolysis units, gets split into oxygen and hydrogen again, and part of the loop closes. The methane can be stored as a potential fuel or vented if you don't have a use for it yet. CO2 sensors in the habitat track concentration down to fractions of a percent, and the control system adjusts scrubber flow and Sabatier operation to keep the number inside tight limits. Even if air and water loops are tight, you still have the most obvious question left. How do you feed people in a place where nothing grows outside and grocery shipments are weeks or months away? A human needs roughly 2,000 to 2,500 kilocalories per day, depending on workload. If you ship that as dry food from Earth, you're talking about 0.6 to 0.8 kilograms of food per person per day. For 4 people, that's roughly 2.5 to 3 kilograms per day, close to a ton every year. That's a lot of launch mass just for food, even in compact dehydrated form. In early missions, most of the calories will come from cargo, pre-packaged, shelf-stable meals designed to last months without spoiling. But to reduce that burden and improve quality of life, you add local growing systems, even if they don't cover all your needs at first. Hydroponic or aeroponic setups let plants grow with roots in nutrient solution or mist, under LED lighting tuned to the right wavelengths. Leafy greens, herbs, small vegetables, and eventually more calorie-dense crops can all be grown this way. Realistically, the first house might only produce 10 to 20% of its calories locally, but that's still important. Fresh food has vitamins that can degrade in long-stored rations, it breaks the monotony of packaged meals, and it gives crew something alive to care for in a dead environment. Over time, as you add more growing area, better lighting, and more efficient nutrient recycling, that fraction can creep up, but getting to full food independence takes a lot of space, power, and research. All of these systems, oxygen generation, water recycling, CO2 scrubbing, food production, sit on top of one final, absolutely non-negotiable rule: anything that keeps you alive must not have a single point of failure. You don't fly one oxygen generator, you fly several. For something critical, you might run 2 units active and keep a third as a cold spare, powered off until needed. Same with CO2 scrubbers, water pumps, main fans, and key sensors. In engineering shorthand, that's N+2 redundancy, where N is how many units you need to meet demand, and you have at least 2 extra on top. Even if 2 units fail, the system still keeps up. This makes the house heavier and more complex. You double or triple plumbing lines, you add extra cabling, you carry more spares. But when the closest repair shop is 3 days away by spacecraft, over 384,000 kilometers, and you can't just open a window, that overhead is not a luxury, it's a survival rule. You also test failure modes hard. What happens if a main pump seizes, if a valve sticks open, if a filter clogs? Does the system fail safe, or does it quietly drift toward danger? The design has to catch problems early, switch to backups automatically, and give the crew clear, simple instructions on how to fix or bypass broken parts. So by the time the life support loop is stable, you've turned the first lunar house into a tightly controlled ecosystem, where every breath, every sip of water, every meal, every gram of exhaled CO2 is accounted for, processed, and fed back into the system. But even with all that, you still face one brutal practical limitation. You can't afford to have humans in suits doing heavy construction work outside 4 hours every day. They're too slow, too fragile, and too expensive. That means one last escalation: before and after the crew arrives. Most of the real building is done by machines. So the next problem is, how do you field a construction crew made almost entirely of robots when every command from Earth arrives too late, and the environment outside will happily destroy anything with moving parts that isn't built for the abuse? Out on the moon, most of the real work has to be done by machines, not people in suits. And the main reason is simple. Your brain is always at least 1.3 seconds late if you're on Earth. Light needs that long to cover the 384,000 kilometers between Earth and Moon, about 240,000 miles. So if you try to steer a bulldozer in real time from a control room on Earth, you move the joystick, nothing happens for 1.3 seconds, the bulldozer finally reacts. Then you see the result 1.3 seconds after that. Any quick correction you try to make is always chasing the past. In a tight space or near expensive hardware, that's a recipe for collisions and stuck vehicles. So lunar construction robots can't be dumb remote control toys, they have to be at least semi-autonomous. From Earth, or later from a control room on the moon, you give high-level commands, grade this area to a 1% slope, dig a trench here 1/2 meter deep, move these loads from point A to point B. The robot plans the path, watches for rocks, keeps its blade level, and handles small adjustments on its own. It sends you status updates, alarms when something's off, and progress reports, but it doesn't wait for approval every time it needs to turn its wheels a few degrees. That means the hardware itself has to be built like a real piece of construction equipment, just shrunk and adapted for 1/6 G and vacuum. Picture a medium-sized lunar bulldozer or loader, something in the 1 to 2 ton mass range, like a small car on Earth. It runs on electric motors, not combustion engines, pulling 10 to 20 kilowatts of power, roughly what a small house might draw at peak. That power can come from thick cables plugged back into your base's grid, or from big battery packs that it swaps at a charging station. In 1/6 G, a 2-ton machine only weighs the equivalent of about 3.3 kilonewtons, or a third of what it would weigh on Earth. But the mass is still there for inertia, and with the right tracks and wheels you still get enough traction to push and carry cubic meters of regolith per hour. Tracks or wide wheels are important. You don't want the vehicle to dig itself into the soil. Large contact patches spread out the load, keeping ground pressure low so that the machine rides on top instead of cutting deep ruts. Suspension is simpler than on Earth. You don't have potholes and mud, but you do have rocks, slopes, and low gravity that can turn a bounce into a long, slow hop if you're careless. So speed will be limited, but payload and pushing power will be high enough to get real work done. Early on, these robots will behave a lot like Mars rovers do now, cautious, slow, and heavily supervised. Every move is planned, their software is conservative, and operators on Earth or in orbit watch their progress closely. That's fine for scouting and small tests, but it's nowhere near enough if you actually want a full house printed and buried before humans land. To build a base at scale, you need a step up in autonomy and in coordination. You're talking about fleets of machines, each with a specific job. One excavates, another hauls material, another handles 3D printing and sintering, another sets down power cables or compacts the soil. They need to share maps of the terrain, avoid running into each other, and adapt when one gets stuck or breaks down. They'll carry LiDAR units and stereo cameras to build 3-dimensional maps of their surroundings, including slopes, rocks, craters, and already built structures. Onboard software compares what the sensors see to a shared base map, updates it, and plans safe paths in real time. From mission control, you might see a live map with icons moving around, and you'll set goals like complete this berm or finish this landing pad, while the swarm figures out the best way to divide tasks and sequence moves. All that intelligence doesn't matter if the hardware dies after a few months because of one enemy you can't escape: lunar dust. Every joint, bearing, and seal on a robot is a path for dust to creep in. The grains are sharp, they're abrasive, and they can carry static charge. If they get into a gear or a hinge, they slowly grind and jam it. If they build up on sensors, they block cameras and LiDARs. Over time, a high-value machine can get crippled by what looks like a thin grey film from the outside. To survive that, lunar construction robots are dust-hardened from the start. Actuators are sealed, with labyrinth seals or flexible boots over moving parts. Designers avoid unnecessary exposed gears, instead using enclosed gearboxes, magnetic couplings, or even direct drive motors where possible. Surfaces near joints might have sacrificial covers, panels meant to take the dust damage and be swapped out during maintenance. Optical systems get their own protection. Lenses sit behind clear covers with wipers, airless brush systems, or electrostatic dust removal coatings that use electric fields to push grains off the surface. Filters and small vacuum systems may pull dust away from critical inlets and vents. Any place dust can rest, clump, and then fall inside when a cover opens is analysed and redesigned. Even with all that, robots will still break. A jammed hopper, a burned-out motor, or a sensor glitch will stop work. That's where humans, once they arrive, come back into the loop, not as drivers, but as field mechanics and supervisors. When you're living in the house, you don't spend your days sitting in a loader cabin. You stand in a shirt-sleeve control room or at a console inside, watching multiple robots through their cameras and map feeds. You assign tasks, adjust priorities when something unexpected shows up, and respond to alarms. Sometimes the machine can't fix itself. A hopper might be clogged with compacted regolith. A track might have jumped off its guide. A dust cover might have torn. Then someone suits up, goes out with tools and does targeted work, clearing a jam, bolting on a spare part, swapping a battery pack or a motor unit, recalibrating a camera. A few hours of human-either time can recover dozens or hundreds of machine hours that would otherwise be lost. Inside the base, workstations let you run diagnostics, push software updates, and run simulations before new behaviours go live. You don't want a bug in a driving algorithm causing a bulldozer to clip a habitat wall. So test first on virtual terrain, then on a safe test patch, and only then near the critical infrastructure. The relationship becomes clear. Fragile humans inside a carefully controlled pressure bubble, rugged but not invincible robots outside, grinding through dust and vacuum. Most of the physical progress, moving rock, printing shells, laying cables, comes from the machines. Most of the planning, troubleshooting and fine-tuning comes from people. It's a partnership where every extra bit of human exposure outside is dangerous, but also extremely valuable when focused on the right maintenance or rescue task. But there's one more twist connecting all of this to survival. Every time those robots move, every time you walk outside in a suit, you're kicking up that same dangerous dust. If it makes its way into the air inside your carefully sealed house, it stops being only a mechanical problem and becomes a direct health threat, grinding into lungs, eyes and equipment. And unlike on Earth, there is no rain, no wind, nothing to wash it away, so the next challenge is brutally personal, not just how do machines live with this dust, but how does your own body survive it? And how do you design doors, suits and cleaning systems so that the thing you're building your house from doesn't end up destroying the people living inside it? The ground you're building on isn't just rough on machines, it's actively dangerous to your body. And once it gets inside the house, it becomes a health problem that no one can walk away from. Lunar dust looks soft in photos, but at the grain level it is harsh. Typical particles are tens of micrometers across, on the order of the thickness of a human hair. But they are not smooth, rounded grains like beach sand. There are jagged fragments, smashed by impacts, full of sharp edges and points. There's no water or wind to wear them down. On top of that, they pick up electrostatic charge from solar radiation and friction, so they cling to anything that moves through them. Apollo astronauts saw this up close. Dust stuck to suits like a layer of black soot, but when they touched it, it felt abrasive like ground glass. It scratched helmet visors, it worked its way into zippers and joints, it left stains and marks that didn't brush off easily. That was after just a few EVAs, a few days on the surface. For a permanent base, you're dealing with this every day for months and years. Outside, that's mostly a mechanical problem. Inside, if you breathe it, it becomes something worse. On Earth, fine dust in mines and factories is known to cause lung diseases like silicosis, where particles get lodged deep in your lungs and your body reacts by building scar tissue. Over time, that destroys lung capacity and can lead to serious permanent damage. Lunar dust is at least as bad, and probably worse. Its sharp edges cut and irritate tissue, and its freshly fractured surfaces can be chemically reactive. You do not want those grains embedded in your lungs or eyes, so the rule is simple: dust stays outside. Inside the house, air filtration has to be able to capture particles down to just a few micrometers across. Similar to or better than high-grade HEPA filters, air circulates not just for comfort and CO2 control, but to constantly strip out any dust that sneaks in, trapping it in filter media that gets swapped and disposed of carefully. To keep the load on those filters low, you redesign how people even enter and exit the habitat. After every EVA, you can't just walk back through a door and knock your boots on the mat. One strong approach is suit ports or external suit garages. In that system, the suit stays outside, docked to the hull. The back of the suit is a hatch. You open the hatch from the inside, climb straight in or out, and when you close it, the dusty exterior never crosses the pressure boundary. All the grime stays on the vacuum side. If you use more conventional airlocks with suits stored inside, then you need aggressive de-dusting protocols in the lock itself. Brushes, vacuums, air jets, sticky panels, all designed to pull dust off the suit before you open the inner hatch. Either way, the goal is strict. As little lunar dust as possible ever reaches the main hab volume. That same dust is also ripping apart the suits that keep you alive outside, and Apollo already proved how fast the damage can happen. During the Apollo missions, suits degraded significantly over just a handful of days. Dust got into fabric layers, grinding fibers, it scratched visors, degraded seals, and added friction to joints and zippers. Those suits were designed for short missions, they did their job, but they showed clearly that the moon's surface environment will chew through gear if you let it. For a permanent house, where suits might need to last hundreds of hours of EV time, not just tens, you need either much more dust-tolerant suit designs, or you need to reduce how often suits have to flex and open. Rear-entry suits that stay outside with rigid torso shells and protected joints are one answer. They keep their dusty outer layers in vacuum and limit how much you bend and twist the soft parts. Every moving joint gets harder materials, better seals, and maybe sacrificial bearing surfaces that can be swapped out. Cables, hinges, boots, and gloves all need to be built for abrasion. Even then, suit maintenance becomes a regular scheduled task, not an afterthought. If a suit fails on an EVA because a dust-damaged joint locks up, that's not an equipment issue, that's a rescue operation in progress. The base itself also needs ways to keep dust off critical surfaces without sending people out with brooms and brushes all the time. That's where electrostatic cleaning comes in. Engineers are already testing electrostatic dust shields, surfaces that use oscillating electric fields to kick charged particles away. You put transparent electrodes on a panel or window, then drive them with a voltage pattern that pushes dust off the surface. On the moon, that could protect solar panels, radiators, viewports, and sensor windows. Instead of sending a rover out to wipe panels every few days, you flip a switch and let the electric field do the work. For this to be useful, those systems have to survive real conditions. Years of ultraviolet radiation from the sun, temperature swings, radiation, and micrometeorite hits, all while consuming only tens of watts. They need to fail gracefully too. A dead dust shield shouldn't suddenly short out or cook nearby cabling. It should just quietly stop cleaning so you can switch to backup methods. Even with all the high-tech defenses, some dust will inevitably reach the inside, and then normal cleaning stops being normal. In 1/6 G, dust doesn't settle the same way. On Earth, heavier particles fall out of the air quickly. On the moon, everything falls slower, and even a small kick from a footstep can send grains on long, slow arcs across the room, or keep them hanging in turbulent air for longer. Vacuuming becomes trickier. You have to make sure your vacuums don't just blow fine dust out the exhaust somewhere else in the cabin. So you combine several measures. Sticky mats near airlocks grab dust from boots. You enforce no loose items rules, so things that can shed fibers or trap dust are limited. Air filters are upgraded and regularly changed. Surfaces are chosen to be easy to wipe and hard for dust to cling to. Housekeeping feels less like weekend chores and more like hospital or cleanroom protocol with checklists and schedules. People will have to get used to this. Simple actions like shaking out a cloth or slamming a locker door become things you think twice about, because they might send a little cloud of dust floating through the air. You'll probably measure indoor particle concentrations the way we now check smoke alarms, and you'll track how well your cleaning schedule is working over time. So even inside your supposedly safe, pressurized, shielded house, you live with a constant low-level threat from this grey powder that wants into every crack, every lung, every piece of equipment. That invisible pressure, day after day, stacks on top of the physical risks, and it doesn't just wear down hardware, it wears down people. Because once the structure is stable, the air is clean, and the systems are running, you finally hit the last set of problems that no amount of steel or regolith can fully solve. How your brain and your mood cope with living in a buried can, under constant rules and constant risk with the rest of humanity a few light seconds away. Even if every machine works perfectly, the house can still fail you if your brain slowly stops coping with the environment. You're not just engineering metal and regolith, you're engineering how people sleep, focus, and stay sane in a place that doesn't match any of your built-in rhythms. The moon's day is about 29.5 Earth days long. If you relied on outside light, you'd get almost 2 weeks of daylight, then almost 2 weeks of darkness. Your circadian clock, which is tuned for roughly 24 hours, would drift badly. Sleep would get messy, hormone cycles would get out of sync, and performance would drop. So the house has to fake a normal day for your brain. That means LED panels acting as artificial sky. In morning hours, they put out brighter, blue, rich light, the kind that tells your body it's time to wake up. At midday, they stay bright but shift to a more neutral white. In the evening, the spectrum shifts warmer and dimmer, signaling your body to wind down. At night, lights drop to very low levels or full darkness in sleeping areas, except for minimal safety lighting. You might run on a 24 or 25-hour internal schedule, depending on what long-term studies say works best. But the key is consistency. Wake, work, exercise, meals, and sleep all follow a pattern regardless of what the sun outside is doing. That structured light cycle, backed up by schedule discipline, helps reduce insomnia, mood swings, and the slow cognitive decline that comes from living in a timeless cave. Space itself is the next pressure point. Technically, people can live and work in very tight quarters. Submarines and the ISS prove that. You can squeeze a person into 10 to 15 square meters of personal space, around 100 to 160 square feet, and they will function. But over months, cramped space increases stress, conflict, and errors. For a long-term lunar house, that's not good enough. A serious design target is more like 25 to 50 square meters per person of total habitable volume, roughly 270 to 540 square feet. That's not just one big open hall, it's broken up into zones. Small private sleeping cabins, shared work areas, a dedicated exercise space, a galleon eating area, and maybe a small quiet room or window room. The ability to move a few steps without bumping into someone, to close a door and be alone for a while, becomes a health metric, not a luxury. Noise is another constant stressor that most people forget about until they lose quiet. In a sealed habitat, life support fans, pumps, compressors, and electronics are always running. On the ISS, background noise levels hover around 50 to 60 decibels, like a busy office. You can get used to it, but it wears you down, especially if you never get a break. Sleep quality suffers, concentration drops, so from day one, the lunar house needs acoustic planning. Loud equipment goes in separate racks or rooms, with sound-absorbing panels around them. Vibration-isolated mounts keep pumps and compressors from shaking the structure and turning walls into speakers. Air ducts are designed to move enough volume without whistling. You set quiet zones where noise is kept as low as you can make it, especially around sleeping cabins. Silence, or at least something close to it, becomes something you design into the architecture, not something you get by accident. Visual connection to the outside also matters. Real large windows are a structural and radiation headache. They're weak points against impacts. They leak heat, and they're harder to shield from radiation. But sealing people in a tube with no direct sense of the outside world for months is psychologically brutal. Compromises look like this: small, thick viewports with heavy shutters that stay closed most of the time. When radiation levels are low, or for planned periods, you open the shutters and let people look out at the actual landscape. Grey regolith, black ski earth hanging above the horizon. At the same time, you use high-resolution displays inside the habitat, driven by external cameras. Those can show a real-time panorama, zoomable views, or even multispectral images of the surroundings. It's not the same as standing on a hill, but it gives your brain a sense of place, a reminder that you're not just in a windowless lab floating nowhere. The mental load of living there is heavy. You're isolated, confined, and every big mistake could be fatal. Communication with Earth has that 2.6 second round-trip delay, so even conversations with family feel slightly off. If the schedule is relentless and the environment is always shouting danger at you, stress builds up fast. That's why psychological health has to be a design input from the beginning, right alongside power budgets and structural loads. The house needs private zones where someone can decompress alone. It needs shared spaces designed for group activities, not just for work, so the crew can eat together, talk and relax. Entertainment systems matter. Movies, games, books, creative tools, anything that lets people mentally step away from checklists for a while. You also build structured communication into the routine. Regular video calls with family, scheduled debriefs with support psychologists on Earth, and clear time off that isn't constantly interrupted by minor alarms. Crew selection and training are part of this too, but the building still plays a big role. Cramped, loud, ugly spaces magnify every small irritation. Thoughtful layout, light, colour, and sound treatment can soften that. And yet, even if you get all of that right, sleep cycles, personal beer space, noise, views, social structure, the environment doesn't stop being lethal. A fire, a sudden pressure leak, a main power failure, or a medical emergency still has only one outcome if you haven't built the house to absorb shocks and keep going. So after you've made a place your brain can stand to live in, you face the hardest design layer of all, shaping that same house so that when the worst case events finally hit, because sooner or later they will, it doesn't become your tomb, but buys you enough time to fight back and survive. How do you design a house so that when something finally goes wrong, it doesn't kill everyone in the first 5 minutes? On the moon, safety isn't a checklist at the end, it's the core of the design, because every accident happens inside a sealed can with nowhere to run. Start with fire, because it's one of the fastest ways to lose a habitat. In a closed environment, even a small fire can turn deadly quickly. It eats oxygen, raises temperature, and fills the room with toxic smoke and fumes. There is no open window, no outside breeze, no fresh air rushing in. If you don't stop it in minutes, it can make an entire module unbreathable. So you attack the problem in layers. First, you choose materials that are hard to ignite and that don't release clouds of poisonous chemicals when they do burn. Cables, wall panels, seat cushions, clothing, all are tested for low flammability and low toxic output. You don't bring cheap foam or random plastics just because they're comfortable. Then you build in fire suppression. Instead of big sprinkler heads dumping water everywhere, you use targeted systems. Inert gases can smother flames without soaking electronics. Fine water mist can cool and knock down a fire fast, using less water and creating less damage than a solid stream. Specialized foam might protect high-risk spots like power racks. Every cabin has emergency masks and portable extinguishers within easy reach, and every crew member drills fire response until it's automatic. Even if you can extinguish a fire, you still have to keep it from taking the whole house down with it, and that's where compartmentalization and bulkheads come in. The habitat is broken into pressure zones and segments, connected by hatches and short tunnels. Sensors in each section track pressure. If one module suddenly starts dropping from, say, 70 kilopascals down to 30 in a few seconds, the system assumes there's a rupture or a major leak. Alarms kick in immediately. Automatic doors slam shut to isolate that zone. Fans change direction, or shut off to avoid pushing air and smoke from the damaged module into the rest of the base. The crew has clear instructions: who moves where, which route is safest, which hatches to close manually if the automatic ones fail. The goal is strict. Any single breach, any one puncture, must not be able to drop pressure or spread smoke through the entire house. You sacrifice a compartment if you have to, but the rest stays intact. All of that depends on keeping power flowing, because without electricity, doors don't close, sensors don't report, and fans don't move air. So you need a plan for when your main power plant glitches, trips, or fails hard. If your main solar farm or reactor goes down, you don't want the lights and life support to just shut off. Batteries and possibly fuel cells take over instantly, but they have limited capacity, so the habitat switches into an emergency dark mode. Non-essential systems go offline, cooking equipment stops, non-critical lab gear shuts down, lighting drops to minimum safe levels, entertainment systems go black. You might cut total power draw from 15 kilowatts down to 3 or even less. That stretches your battery reserves from a few hours to many hours or even days, depending on the design. Every watt is triaged. Life support, communications, basic lighting, and essential heating or cooling stay. Almost everything else pauses. Crew follow a streamlined procedure to stabilize the situation, check the power plant, and decide whether to attempt a restart or switch to long-term emergency mode. But what if the emergency isn't just power or pressure? What if it's a full habitat fire or a structural problem, and staying in that module is worse than leaving? On Earth, you'd run outside. On the Moon, outside is a vacuum that kills you in seconds without a suit, so evacuation has to mean something very different. The base is designed from the start with safe refuges. That might mean other attached modules that can be sealed off and support life alone, or a separate backup shelter 50 to 100 meters away, around 160 to 330 feet, connected by a pressurized tunnel or reachable quickly by EVA with pre-staged suits. Drills practice both scenarios. In one, you get a warning, grab masks, close hatches, and move through connected modules to a safe area. In the other, if a module has to be abandoned completely, you suit up in record time, follow a marked obstacle-free path, and move to the backup shelter outside. Suits and emergency gear along that route must always be ready, charged, checked, and easy to use under stress. You don't want to be hunting for a missing glove when smoke alarms are blaring. Even if you reach a safe zone, you still have to deal with injuries and illnesses with no hospital down the street. Medical capability becomes part of the house's core hardware. The base needs a dedicated medical bay, not just a first aid kit. That includes monitoring gear for vital signs, oxygen supplies, defibrillators, basic surgical tools, and medications for common issues and known risks. Bone fractures, burns, decompression incidents, radiation exposure, infections. At least one crew member must be trained to paramedic level or beyond, and others need enough cross-training to assist in an emergency. Telemedicine links back to Earth doctors' help, but that 2.6-second round-trip delay is real. In a cardiac arrest, a depressurization injury, or a severe allergic reaction, you can't wait for a committee on the ground to debate options. The local medical lead makes the initial calls, stabilizes the patient, and uses Earth support for guidance once the immediate crisis is controlled. All of this means the first lunar house is designed with failure in mind from the very beginning. You assume lines will leak, joints will crack, things will catch fire, humans will make mistakes, and then you build layers of defense so that any one error or event doesn't cascade into total loss. You compartmentalize structure, atmosphere, power, and even daily routines so that when something breaks, there's always somewhere else to go, and some other system ready to take over. And if you manage to do that, if your first habitat can survive years of normal operations plus the rare emergencies, you're no longer just visiting. You have a system robust enough that you can think about expanding it, repeating it, and eventually scaling from one house to a neighborhood, then to a real lunar town, powered and built mostly from local resources. So the final question becomes the biggest one of all. Once you've proved you can keep a handful of people alive in one hardened bunker on the Moon, How do you turn that fragile outpost into a self-growing settlement, with multiple power plants, factories, transportation networks, and enough redundancy that even losing an entire module, or even an entire house, no longer threatens the human foothold on that world? What really changes the day your first lunar house stops being an experiment and just quietly works day after day? At that point, the question is no longer, can we survive here? It's, how fast can we scale this up before some bottleneck chokes us? The first bottleneck you attack is power. One house might live on 10 to 20 kilowatts, the output of a small generator back on Earth. A village does not. As you add habitats, rovers, drills, 3D printers and labs, you're aiming for hundreds of kilowatts, then megawatts. That means your solar farm grows from a patch the size of a basketball court to fields covering thousands of square meters, tens of thousands of square feet, spread along ridges that see the sun most of the time. Reactors scale too. Where you started with a single 10 kilowatt class unit tucked behind a berm, you move to multiple reactor modules, maybe 50 or 100 kilowatts each, paired with much larger battery banks. You don't rely on one plant. You create a local grid where losing any one source doesn't black out the settlement. In situ resource utilization plants follow the same curve. Early hardware might make a few kilograms of oxygen per day from water ice or regolith, just enough to give you margin on life support. As you add bigger reactors, more electrolysis units, and refined processes, you push that to tens, then hundreds, then tons of oxygen per day. At that level, you're not just filling habitat tanks, you're filling lander tanks. Crewed and cargo vehicles arrive empty and leave full, refueled with lunar oxygen and eventually lunar-derived hydrogen. That unlocks regular traffic between orbit and surface and between different sites on the moon itself. But oxygen is only one side of the chemistry. The moment you start pulling serious amounts of it out of the soil, you're left with a growing pile of metal byproducts. The obvious question is, do you treat that as waste, or do you turn it into the skeleton of the next generation of habitats? Molten regolith electrolysis doesn't stop at oxygen. When you melt lunar soil and run current through it, you also separate out metals: iron, aluminum, titanium, and others. At first, you might literally stack those products as ingots, proof that the process works. Then you start feeding them into local fabrication lines. You set up 3D printers and machining centers inside sheltered bays. That equipment takes metal wire, rods, or powder made from those ingots and turns them into real parts: brackets for radiators, replacement gears for rovers, structural beams for new shells. As capability grows, you move from small components to large panels, truss sections, and eventually pressure vessel segments that can be welded or bolted into new habitats. The first house, which started as a single imported can under a regolith arch, becomes the core of a small industrial park. One bay handles metal printing and machining, another assembles and tests new robots, a third refurbishes worn-out tools and suits. Instead of waiting months for a launch from Earth when a part fails, you pull raw material out of the soil, run it through the plant and install a locally made replacement. That shift from fly everything to make it here is what lets the settlement grow without every upgrade blowing up your launch schedule. Once you can build more machines and more habitats on site, the next limitation is distance. How do you move people, water, oxygen and hardware efficiently across a world where there are no roads, no air, and walking in a suit is slow and risky? You start building real transportation networks. Pressurized rovers get bigger and more capable. Early ones might have ranges of a few tens of kilometers. As infrastructure matures, you aim for vehicles that can travel 1,000 to 2,000 kilometers between major maintenance stops, roughly 600 to 1,200 miles, acting as the trucks and buses of the moon. Inside, they're shirt-sleeve environments with seats, workstations and bunks, not simple buggies. Along key routes you place depots, power hookups, spare parts, emergency air and water, and maybe small shelters. Power relays, cables, beamed power links, or local reactors support operations along mining corridors between sunlit ridges and shadowed ice craters. In rough terrain or where ground travel is too slow, you supplement ground vehicles with small rocket hoppers. These are reusable landers scaled down for cargo, able to move a few hundred kilograms at a time from crater floors up to ridgetop depots in short, high-arc flights. They burn locally produced propellant and turn otherwise isolated sites into part of a linked network. Over time, you start to get something that looks like a genuine logistics system: regular routes, schedules, and backup options. Once moving goods and people becomes routine instead of a mission event, the next shift is inevitable. You stop talking about the crew like a single tight unit and start talking about population. The first house holds 4 to 6 people. When that works, you add a second habitat a safe distance away, then a third. Suddenly you have 10 to 20 people on site spread across multiple modules. Redundancy changes scale. Instead of just 2 pumps per system, you now have 2 fully independent houses, each with its own life support, power tie-ins, and shelters. A major failure in one module might force an evacuation, but the others keep running. As industry and power grow, dozens of residents become realistic. Some houses stay focused on operations, control rooms, machine shops, labs. Others skew towards a living space with more generous personal quarters, better exercise areas, and upgraded common rooms. New arrivals might rotate in and out like expedition crews, while a core group stays long-term as the base's institutional memory. At that stage, redundancy of habitats is as important as redundancy of valves. Losing one pressure shell to a structural failure or a freak impact becomes a serious event, but not the end of the entire presence. People relocate, spare capacity in other modules gets used, and you rebuild. The settlement starts to resemble a small town with multiple neighborhoods, not a single cabin in the wilderness. And when you reach that point, running multiple houses off local power, using local materials, moving people and cargo on local networks, you hit a realization that's bigger than any single system. You've created a pattern that doesn't depend on Earth staying involved at every step. When you can build a functioning house on the moon out of lunar dust, power it mainly with moon-based energy, breathe oxygen pulled from rock and ice, and repair your own tools and structures without waiting for a launch window, you've crossed a line. You're no longer just visiting space. You've shown that home is something you can export. The engineering tricks you used here, regolith printing, compact reactors, closed-loop life support, or autonomous construction swarms, pressurized surface transport, can all be adapted. Mars has different gravity and atmosphere, but the logic is similar. Asteroids have different resources, but the ISRU mindset still applies. The moons of Jupiter are harsher, but the same core ideas, buried habitats, heavy shielding, robust power, carry over. Every later settlement will borrow from the first one that made this work, the first house dug into grey regolith, 384,000 kilometers from Earth, in a place that started as a physics nightmare and ended up as proof that humans can turn even that environment into stable, repeatable infrastructure. At that point, the story stops being about one base on one world and becomes about something larger, a civilization that knows how to push its own definition of normal living conditions off the surface it evolved on and out into the rest of the solar system. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.